experience for you to go. If you haven't been yet, it's highly recommended. There's 200 plus technical sessions, networking opportunities. You can get a $150 discount by using our virtual chapter code, which is located in this slide. All the slides from today will be uploaded on the IMVC site by the end of today, along with the presentation. Here's some of the virtual chapters we have. There's virtual chapters virtually for every topic of SQL Server. Data science, administration, fundamentals, anything you want to know about SQL Server, PASS will have a virtual chapter for it. Join as many as you want. Most of them hold meetings throughout the year, at least once a month. It's a great organization. Please get involved. Here's some of the virtual chapter meetings that are coming up. Unfortunately, these ones are all done already. Here's a couple here. Here's ours today. Excel BI is coming up tonight, and Cloud is coming up tonight. Business Analytics, DBA Fundamentals is on the 21st. All of these rarely available, free to attend. Check them out. Some SQL Saturdays coming up. South Florida is coming up this week, and the following week is Puerto Rico. International, we have Rio de Janeiro, Iceland, Dublin, and Sri Lanka. Great stuff there. We cannot exist in PASS without volunteers. If you're interested in volunteering with PASS, please go to volunteer.sqlpass.org. There's plenty of things that get involved. It doesn't have to be a virtual chapter. It could be for your local chapter, helping them set up SQL Saturdays, arrange local user group meetings. All the help we get is very appreciated. And with that, Warner, are you ready to go?
Yep.
Okay, let me pass you presenter, and we'll get started. Okay, it's switched over.
Okay, so you guys should be able to see my screen in like a second.
Yep, we can see it.
Okay, so let's just get started then. So welcome everybody. I'm really glad to be presenting here for the in-memory virtual chapter. This is actually the first time I'm presenting with the in-memory virtual chapter. So very exciting. It's always interesting to talk about the in-memory technology because it's still not really spread over many installations. A lot of people are kind of confused as to how to approach it or see it as risky or don't really understand where the actual benefits are. So I tried with this session to try to dispel some of those confusions, try to make it really straightforward and give you some ideas of where you might be able to fit this technology into your organization and your SQL servers. So about me, I've been working with SQL Server for about 10 years now. It's going to be 11 this year. I used to be a level 3 DBA at Hewlett-Packard. I'm a principal consultant now at Pythian, which is a managed services IT consulting company out of Ottawa, Ontario. I'm a SQL MCM. I'm a Microsoft Data Platform MVP. You guys feel free to reach out to me on Twitter at warchaff, or if you have any follow-ups after the session, you think about something, you want to get my opinion, my advice, or any recommendations, feel free. Just shoot me an email at warner@sqlturbo.com. I might not answer like super right away, but I usually have, about a 24-hour turnaround time for those. If you want to check out my blog as well as sqlturbo.com, and if you want to check my company's website, just check pythian.com. So the agenda, like I said, what I want is to provide a practical guideline on finding use cases for in-memory or OLTP on our systems. And so we also have some expectations of what is the type of improvements that we can get and why we get those improvements. Some of the issue that I had with the marketing material that Microsoft put out back in 2014 when the first release of Hackathon was coming out was all the claims about, you just have to basically enable this, run this. It's like pressing a button and your whole system is going to run like, turbo boost. Everything's going to be faster, 30x faster, all these claims that, they might be true on specific workloads, specific sets of hardware, and so on, but they are really hard to actually take from these general claims to specific when there's so many different type of uses and workloads that our clients have and that you guys will have on your own systems, right? So first we're going to do an intro of the what, the why, and the when should use in-memory OLTP, and the compromises that exist on it in 2014. I have updated the slide deck as well to include all the improvements that are now available in 2016. The demos will be done in 2014 just because I haven't gotten the chance yet to build a VM with 2016, but hopefully, in the next couple of months I'll get a chance to do that. But the demos themselves, like I said, they're 2014, but the use cases do not change at all for 2016. First demo use case, we're going to talk about what I call the dials of in-memory and durability. So some people think that in-memory is a 0-1 proposition. Either I have zero investment on in-memory, or I have 100% investment on in-memory, and that's not the truth. It's kind of like a dial where you can invest a little bit on in-memory, you can invest a little bit more, you can invest a little bit on in-memory and tweak durability, and then you can invest 100% on in-memory and 100% on zero durability. And we'll talk about what the use cases are for that, of course. Then we're going to do another demo on use case, the one that's called the landing pad. The SQL cat team sometimes call this as the shock absorber, and it's basically just to show the capabilities of in-memory of ingesting data pretty quickly compared to a classic table. And finally, I'm going to talk about another use case that doesn't really get that much attention and didn't get that much attention in the marketing material, and is the fact that table variables can be all in memory as well. And while that really depends on the workload, if it's going to be a big issue or not, like I said, depending on the workload, it could mean that with very minor changes, you could have a big boost in your workload, just basically because of the change of moving from classic table variables to 100% in-memory table variables. And then finally, we'll just wrap it up with a very general workflow that I apply when testing this technology with clients, and I recommend you guys apply on your own environments as well. So let's talk about the fundamental premises, or why in-memory OLTP was seen as a good investment to Microsoft, right? Why would they bother putting all this money into research and development and creating this new feature, a new storage engine basically inside SQL Server? So the basic premise number one is that CPU speed is now stagnant. It hasn't really gone over in the last years. I don't know if you can probably go find some chart of the history of Intel microchip speed, and you will be able to see that an overclocked CPU right now probably taps out at 4.1, 4.2 gigahertz, and it's not getting faster, right? It's not like Intel is not announcing a 6 gigahertz CPU clock. Like, that's just not happening, right? There's issues now with how small they can go on a single core, and the issues with dissipating heat, and the issues with how many transistors they can pack in such small space, where the clock speed itself is not improving, but what they're doing now is putting more cores per chip, right? So the game now becomes not how much faster can we go in one core, but how do we really take advantage of all the parallel processing capabilities on our multi-core chips, right? Second is something that I think everybody here will agree on, is that the cost of RAM continues to decrease and server capacity continues to increase. And not just server capacity, I mean, everybody here in their laptop probably has at least, I think right now it's pretty common to just buy an 8 gig laptop. That wouldn't be anything crazy. My laptop that I use for presentations has 16. I know colleagues of mine that they run a lot of VMs on their laptops, and they're running like 32 gigs of RAM laptops nowadays, right? So this is just laptops or consumer devices, right? Servers have even more capacity nowadays. So we can pack more and more RAM. More and more databases can fit in memory. And then finally is the premise that there are some aggressive optimization algorithms, the ones that use RAM and the ones that use that are used by in-memory OLTP, that have to work on memory, but they can't really work yet on disk. And it's just, even if you have SSDs, even the SSDs themselves are not fast enough to do what you can do on memory for these algorithms. And some of the other things are just not possible to do at all when you go to disk. For example, in-memory OLTP, when it does comparisons to see if a record has been changed or not in memory. It can actually do these comparisons with what's called a compare and swap hardware operation. So this is an actual operation that an x86, x64 chip can do on a memory address. So SQL Server doesn't need to have even to put a lock on these records, because the comparison can be done purely on hardware, right? That cannot be done with a disk device, which is basically just seen as a block on a disk by the OS. It's not the same as a memory address that can be directly addressed by the CPU in the computer, right? So there are algorithms that simply just work on memory, but they would not work on disk. Just to, again, to just give us some perspective on this, spinning metal, usually we talk about latency that can go to milliseconds. Solid state, if you have a really good drive, you can get latency down to the microseconds. And then RAM, you're basically talking about latency that goes to the nanoseconds, right? So there's about 3 orders of magnitude that separates each type of these technologies. And between spinning metal and RAM, right, we have like 6 orders of magnitude, right? We're talking about being 1 million times faster, right? So let's go over the full stack of a SQL Server and review where the improvements are, what were the modules or the sections of SQL Server that were improved or that couldn't be improved when you would deploy in-memory OLTP. Okay, so network protocol, there was no change in network. So if your bottleneck right now is based on your client sucking too much data through the network, then in-memory OLTP is not going to do anything for you. That's not your problem. It's not related to in-memory contention. If the issue is log I/O, well, there are a couple of things that are actually improvements if you deploy in-memory OLTP. So now we have the option of creating 100% non-durable tables. So these tables will just write data to their memory records on RAM and will not be persisted in any way. So if you restart your server, these tables will just keep the schema. The data is all going to be gone. Obviously, we won't want to do this for an actual permanent table that we want to keep forever as part of our application, but it's very useful, for example, for ETL staging. It's very useful, for example, for materializing views. For example, if I have, let's say I'm a gaming company and I have a bunch of leaderboards of people that are playing my mobile game. Obviously, the leaderboards are going to be changing all the time because there's different positions inside the leaderboard. And if I ever, just lose power, let's say, and I restart, I can always compute back the leaderboards from the recorded records of every single player. So, for example, leaderboard would be a good candidate to just cache it as a table in memory, right? Not only that, but even for permanent tables, this is something that also a lot of people don't realize, or it slips by in between all the conversation, is that in-memory tables produce less transaction log in general. For example, when a page split happens in memory, the actual allocation of the pages and the movement of all the records, all that doesn't go to the transaction log because it doesn't matter. All that is saved for memory is the data, but not the index structure, right? So when SQL Server will restart, it will read all the data and then recreate the index structure in RAM. Whereas if we're talking about a permanent table, both the data and the index structure has to be persisted. So that produces more transaction log. Let's see. Sorry, the other way. Data file I/O has been changed, so it's been optimized for streams. It's streams of sequential writes in data and delta file pairs. So basically, there's a set of files. Some of them have the data. So every time you insert, it will go into the data. And there's also for each one of those data files, there's another file called the delta file. And this is the file that will keep the record of what records were deleted. Okay, so if you actually, when you update a record on in-memory OLTP, you're not updating a record in place, you're doing an delete with an insert. That's how it works. The process, SQL Server itself has a process so that if you delete a lot of records, so that mostly, most of the records inside the data file are actually already marked that have been deleted, then it has a process in the background to basically mark them. It's called like the tombstone. It'll mark them, it'll merge with another file that might be somewhat empty as well, and then get rid of, basically create a new pair of data and delta files. So if you have really fast sequential writes, that's what you want for a container for in-memory OLTP data and delta files. There's an improvement in query optimization, which is native compilation was introduced. So instead of being the regular interpreted SQL server, we can actually compile store procedures as actual DLLs. So they get compiled directly into machine code, so the overhead of interpreting is basically removed. Now, native compilation is really tricky in 2014 because the surface area of the T-SQL supported is very small. It's been improved quite a bit in 2016. So, for example, I still haven't had a client in 2014 that used in-memory and did a big investment on native compilation. A lot of them went in-memory for some sections of their database, and some examples I'll give, of course, in the demos, but not many of them went on big investments on spending time creating natively compiled store procedures. 2016, like I said, I expect it is going to change and is going to start to see more adoption because the surface area of T-SQL allowed in a natively compiled store procedure has increased quite a bit. All right, let's see. Let's keep going up on the stack here. Query execution has been improved. If you go with in-memory, remember there is no latching and there is no locking. So there's no locks. Locks obviously being a logical concurrency semaphore, right? So if you grab a lock for a record, it stops me from writing if you're reading from it and so on. Latching is pretty much the same concept, but it's actually on the memory address level, right? So you put a latch on, let's say, for example, even if we have row locks and we're trying to update different rows, we might go through a very short-term latch trying to write to the same memory address if they just happen to be in, like, let's say, the same page in memory. Right, so latching happens even faster than locking, and it's more related to protecting the actual memory addresses. In-memory OLTP, like I said, it has no locking, it has no latching. In SQL Server, sometimes people use read committed, snapshot isolation, or snapshot isolation as a way to get around the locking, but there was really no way to get around the latching. Of course, to have issues with latching, we're talking about really high volume environments where this slowdown of waiting on a latch is actually quantifiable, right? If you are not working on a high concurrency, thousands of requests per second environment, then this particular improvement will probably not do anything for you. Indexing, we have hash indexes for the in-memory table, so that's indexes that can do the equality lookups really fast. All indexes are covering for an in-memory table, which is very interesting, right? We're used to thinking of, oh, I create an index and then I have to add the columns that I actually want from my query so that I try to avoid lookups as much as possible. That's when we're dealing with on-disk tables, right? But in memory, all the indexes always just hold memory pointers to the actual memory addresses that have the data. So all the indexes are considered to be covering all the other columns. Something else, there is no fragmentation to deal with on an in-memory index. If we think about fragmentation, for example, there's basically two types of fragmentation, right? There's one, which is when we have all these pages with really low density in memory, just wasting our RAM because the pages are mostly empty. And then there's also the fragmentation, what we would call external fragmentation, which is the out of order pages on the actual storage, right? So the out of order issue doesn't happen because there is no indexes materialized on disk for in memory, and the low density issue doesn't happen because the algorithms that are used for in-memory OLTP for the indexes already take into account this. And when they're doing operations on an index, if they find like one, in one memory address, one of the pages of the index is very low density, it will try to merge it with another one that's already in memory. And again, these algorithms are possible because all the data is sitting in memory. It would not be possible, or it would be really expensive to do them on disk. So no worries about fragmentation. I know that's one that DBAs really hate having to deal with on disk tables. Memory use gets table variables are finally really in memory. There was a huge myth back in, I don't even remember when was this, back in maybe in 2005, where people said that, table variables are really in memory. And then, you can probably still find some articles online where some people were comparing, table variables to tempdb, and they say, oh, well, table variables are better because they're always in memory as opposed to tempdb. It's like, it's not true. Table variables still get allocations through tempdb. Now they're really in memory, so the tempdb footprint for table variables has decreased quite a bit. So if you have a workload with a lot of table variables, you will be using a lot less tempdb if you go with table variables that are in memory. And there are no copies of the data, just how, if you're doing an index, you have a bunch of different copies of columns depending on how many indexes you have. But you do have to keep multiple versions. So if you're changing a row and somebody else is reading it, the system is going to create another version of the row in memory, and then that's what is going to get changed. So you always have to keep that into account. If you're going to be doing a lot of changes or not, you have to basically budget enough memory to keep not only one copy of the data, but also possibly multiple versions of that data at the same time. And the improvements in CPU is basically the CPU is maximized by eliminating the other bottlenecks. And on top of that, you can also use native compilation. So once you eliminate the locks, once you eliminate the latches, once you don't have page IO latch waits from the disk, there's basically very little to block the CPU from just getting work done. So CPU is maximized by eliminating all these other bottlenecks. If you even need, like I said, if you really think you even need to go further than that, then you can explore native compilation. But it's not a requirement. That's also something that was kind of a misconception that unfortunately was spread a little bit during the release of Hackathon, and it was that, to use in memory you had to have native compilation, and that's not true. Right? Okay, so let's talk about the compromises of V1. It's basically SQL 2014, so there's no partitioning. It does require careful measurement, so how much RAM, the hash buckets inside a hash table, because you couldn't do an alter table, for example. There's no parallelism. There's no foreign keys or triggers or unique indexes. The schema is 100% static. Like I said, you can't do an alter table in any way. And there's very limited T-SQL for native compilation. So improvements in V2, SQL 2016, it supports foreign keys, check keys, unique constraints. We can do natively compiled functions and triggers now. The amount of data that you can put on RAM now has increased from 256 gigs to 2 terabytes, so a lot more data. Transparent database encryption is now supported. So back in 2014, if you enable TDE, it basically would just work on your regular data files, but your in-memory files would not be covered by TDE, so that was a pretty big gap there in encryption, and now it's supported. You can do an alter procedure if you need to change the store procedure, or you can do an alter table if you need to change a table. So finally, the schema is not 100% static, so that's, that's kind of like a scary thing for some people that you can't do an alter table. Well, 2016 now you can. Parallel plans are now possible on in-memory tables, so that's a big deal as well, because before it was always just single core in-memory plans. Now we can do parallel plans on them as well. And the native compilation surface area for T-SQL has increased a lot as well. But now there's outer joins, you can do an OR, you can do a NOT, you can do a union all distinct, and you can use the classic subqueries constructs like in, not in, exist, and not exist, basically all the semi-join and anti-semi-join queries. Okay. All right, so let's talk about the dials of in-memory and durability. I'm going to jump into my VM. Let me find the VM. Okay. And I'll show you guys what I have here. So first of all, I'm going to clear the tables that we're going to use in the demo. I'm going to go through the script and let me put myself in the right database. So I'm going to go through the script, and then we're just going to see the demo. So for anybody that is not familiar with how you set up Hackathon, so first thing you do is you do an alter database, and you add a file group. Just give it a name, and you say contains memory optimized data. Now once that file group is created, you can actually add a file. Keep in mind though, it's not really a file, it's basically a folder name. So if you go back down here, you guys can see mine is just called a VentureWorks Hackathon. And it's not a file, it's not like a VentureWorks Hackathon.mdf or .ndf or anything like that, right? It's literally a folder. And then inside this folder, SQL Server will create all the necessary files and structure to keep all those data and Delta files. Okay. All right, so what we're going to do in this demo is I'm going to run a comparison of Classic with many of the other different flavors. Like I said, the dials that we can touch and tune and tweak for in-memory tables. So here's a Classic table, very, very simple schema what you would see in any type of OLTP system. Business entity ID with an identity 11, person type, a title, first name, middle name, last name, suffix, a primary key clustered on that identity, nothing fancy. I created the same schema here for an in-memory table. You guys can see the only difference is the durability and the memory optimized on. So that's how we just tell SQL Server, hey, this is an in-memory table, right? Memory optimized on, and the durability, I want schema and data. Keep in mind, there's two options. There's schema and data, and there's also schema only if I want the table to be completely non-durable, meaning, you know, restart, data's gone, only the schema's left. Okay. To use in the demo as well, I created this another table that is exactly the same. You guys can see it's memory optimized on. The only difference is this one is schema only. It's not schema and data. Now I created a natively compiled store procedure here as well, where we just doing an insert of one of these tables. I created another natively compiled store procedure here, where we're just going to use the new, well, new in 2014. I guess it's not new anymore with 2016, but in 2014 this was new. Delayed durability equals on. So delayed durability, for those of you that are not familiar with it, it basically means that SQL Server is not going to write to the transaction log right away, but instead is going to either wait for a durable transaction to come in, or is going to wait until the log buffer in memory is full before it writes to the transaction log. So basically, if the data doesn't have to be 100% flushed into the log right away, and you can actually afford the risk of some data loss, then you can turn on delay durability, and it'll just really increase the throughput to the transaction log, because it basically just waits until the entire log buffer is full before it writes, instead of writing every single time. Okay. And then finally, another store procedure, and this time it's the exact same insert, but now we're going to do it into a non-durable table. So this one will be completely in memory. It will not be stored on disk at all. Okay, so what we're going to do is I'm going to run, I already have the SQL query stress files. So I'm going to be running each one of these inserts. So you guys can see here, let me zoom into it so you guys see there I have number 1 is going to be an insert, number 2 is going to be an insert for an in-memory table, number 3 we're going to do an insert to an in-memory table through a natively compiled store procedure, number 4 we're going to do an insert to through the natively compiled store procedure to a delayed durable transaction. And then finally, we're going to do in-memory insert to a completely non-durable table, right? So we're going to be moving from regular classic disk-based, and then we're going to be moving towards more in-memory, less durability until we get to the number 5, which is in-memory, natively compiled, and completely non-durable. And then we'll see what the comparison is in performance between all of these. Okay. So let's just run each one of these. So this is it's running in 200 threads. My laptop has 8 cores, so you get an idea. It's going to do 300 iterations per thread. So at the end of this whole test run, we should have 60,000 inserts that ran against this table. This is the first one. It's the regular classic table. Okay. And I'm going to be recording the client seconds per iteration. So this is the time that it took per iteration to do one of these inserts as seen by the client. So this would be 0.0757. I have an Excel sheet here where I'm going to be recording these. 0.0757. And as we go along with the other ones, I'm going to be recording this same number, and then we can see the differences at the end. So this one is an insert with regular T-SQL. It's not natively compiled to the in-memory table. So again, there's a misconception there that you can only, touch or interact with in-memory if you do native compilation, which is not the case at all. You can definitely work with in-memory just using what they call interop T-SQL, right? And it's completely transparent to you as the user. It simply works. All right, so same 60,000 client seconds per iteration average. That's 0.0321. 0.0321. Okay. Now we're going to move to the next one. It's going to be number 3. It's in-memory insert. This is with natively compiled store proc. Okay. So let's kick that one off. So keep in mind here the natively compiled one is just one insert statement. So what I found is that if your natively compiled store proc doesn't really have a lot of logic inside of it that can be optimized, then sometimes there's not even a performance gain compared to interpreted, or it's a very, very small performance gain compared to interpreted. So let's record the time now, 0.0186, 0.0186. 0.0186. All right. Now let's move into the fourth scenario. This is natively compiled in-memory table, but with delayed durability to the transaction log. So in this example, the log writes are going to be batched to the transaction log. So usually the bottleneck here is basically transaction log throughput, if there is any. And we'll just let that run. Yeah, and it's done. So 0.0029 average per iteration. So you guys can see once we batch transaction log writes, it makes a big jump there in the average time per iteration of the inserts. And now final one is number 5 here. Let me get this out of the way. This one is an insert to a non-durable table. So this is a 100% non-durable insert. So I'm going to insert 60,000 rows. If the server were to restart, these 60,000 rows would just evaporate. They would just not be there at all, right? So again, it's not for permanent data. Full non-durability is only for temporary objects like staging tables, or for caching query results, or for materializing views, or for anything like that, okay? And we're done, and it's 0.0026, okay? So let's just update this here. It's 0.0026. Okay, so if we look at the numbers then, let's do a comparison. So in-memory interop, just same insert statement, just by going in memory, not changing the T-SQL in any way. So we get a 2.3 improvement of the average runtime for one of those inserts between classic and in-memory. If we go native, then we get a 4 times improvement between classic and in-memory with native compiled, right? So it's not a huge leap. This case is really easy because it's just one insert, but if we're talking about large stored procedures, then we get a couple of issues. First of all, the T-SQL covered for natively compiled stored procedures is not really that big, especially in 2014. It's a lot better in 2016. And second, it might not be worth the hassle, right? Because of the improvements that you can get. Like if you can get a 2.3, 2.5 improvement by literally just recreating the table in memory and leaving it with interrupt, then it might not be worth the work to go with natively compiled just to go 1.5 over that type of improvement. Now, if you can identify a table where as long as you have most of the data, the risk of data loss can be tolerated, then you can go delay durable. And at that point, that's where there's a huge, at least in my laptop, right, where in my laptop, basically the transaction, writing to the transaction log is the biggest bottleneck. So once we optimize or remove this completely, it's a huge change in throughput, right? So we're talking about, it's 26 times faster to run delay durable in my laptop than a fully durable, even on natively compiled, right? And then finally, schema only. Instead of 26 times faster, it's 20 times faster. So schema only is going to be, like I said, 100% undurable. It didn't touch the transaction log at all. So we can see where, optimized transaction log here and no transaction log at all. This is where the biggest jumps are in my laptop because the transaction log is the biggest bottleneck in my laptop. If you were to go to, let's say, a server where the transaction log is sitting on SSDs, these particular exercise could look very different, right? So that's part of, again, the proposed workflow of the type of analysis that somebody needs to do when they're thinking about implementing in memory. Okay, so let's go back to the slides. So the use case, if you have lock-in issues and row versioning didn't really significantly improve throughput, so meaning you already tried snapshot isolation or you tried read-committed snapshot isolation, then you could try to just go in memory, and with the reduced lock-in and latching, it could give you a boost in performance. If you don't have lock-in issues, but you still have latching, this is going to be the scenario where it's a server that has a lot of volume. It's not going to be a really common scenario for most people. In general, like I said, this latching, the removal of latching will only impact the biggest shops running the biggest, busiest SQL servers in the world. But hey, if you have one of those, then you can go in memory and remove the latching from happening. If your lock-in and latching are not significant, after you've done that, you already went in memory and you removed the lock-in and latching, but you still feel like you can get some more CPUs out of the whole thing, then you can try to go with native compilation on top of that. If you have to ingest large amounts of data, big spikes and then low periods, you could go in memory and mix with classic, right? This could be receive a lot of data in the morning and then you have a job that will just move it all to a classic table in the afternoon. If you have high throughput data where it's okay if you lose some of the data as long as most of it's there, meaning delayed durability, that's the risk of delayed durability, then that's when you can use that one, and it'll decrease the traffic to the transaction log and improve throughput like we saw in the demo. And if you have data that needs to be queried with the richness of T-SQL, right, like lots of ad hoc search conditions, for example, but you don't need to keep it between restarts, then you can do schema-only tables. Okay? All right. There's a couple of caveats here, just special edge cases that I've run into, so I decided to document them on the slides. If you have non-durable data and you want to scale it out with availability group replicas, you have to use a schema and data table and use delay durability for optimum transaction log performance. Because if you do schema only, it will not replicate the data of the schema-only tables to the other replicas. Okay? All right, so here's a handy little chart just to kind of symbolize the whole concept. So there's basically, you have two um, two different ways of dealing with in-memory tables. They're at the bottom. You can just go with in-memory tables, or you can also add on top of that native compilation. And you also have different types of durability. That would be the axis there on the vertical. So we have durable, delayed durable, and non-durable. And you guys can see there, if I go with an in-memory table and I go with non-durable, basically that is the top left corner. Then what I'm doing is I'm removing all disk I/O, but no data is persisted. So handy little chart here in case you guys want to keep it as reference, and the slides will be available. All right, so let's do the landing pad demo, also known, like I said, as the shock absorber. So this is the scenario where we just want to ingest a lot of data really fast. So let's go back to my VM, and I can close this now, save, close this now, close this now. All right, so here's the SSIS. I'm going to kick off. Basically what we have is a file here. It's 191 megs, so I'm going to import this file into a classic table and into an in-memory table, and then we're going to compare how long each one takes. So I already have this SSIS package, so I'm going to kick it off. First, we're going to kick off the classic. So, first we need to clean up the table, so let's do that first. And I gotta move to the right database. Okay, so the tables have been cleaned up. So they're empty, and I'm gonna kick off the transfer of classic. And let's go to the data flow. We should see some rows going in. So let me zoom into this so you guys can see what we're doing. So I'm reading a flat file. That flat file is moving rows into the balanced data distributor. This is an SSIS component. You can just download it. I think it's on Codeplex. And what the balanced data distributor is that it splits the input into many outputs to take advantage of multiple cores, right? So in this case, I split it into 4 different outputs. All of these go into a classic table. Okay, so this is the classic version. So far it's inserted about 600,000. While that is running, let's just go over the table history. The table schema. So we can see I have basically 2 tables. One is classic, and again, very, very classic information kind of thing that you would be, for example, transferring on, let's say, a business-to-business type of process where one of your suppliers is sending you an order history or something like that, and then they just send it to you via a CSV. Maybe you pick it up from an FTP, or you pick it up through a Win secure copy or something like that, right? First table, all disk-based, nothing special about it, identity 1.1. Second table is exact same schema, the same identity 1.1. The only difference, again, is just the specification that it's memory optimized on, and the durability here is schema and data. I could have made this even schema only, but I just left it as schema and data since, this table is permanent, so they're both permanent tables, okay? Now let's see how far this has gone now. So this is at almost 2 million now. You guys, I'll just zoom in for you. So it's at 2 million rows mark, so it still has about 1 million to go. Now let's think about what this is doing while this is running. So remember, we have an on this table with an identity 1.1. So it is going to try to keep inserting records into that last 1 page of the clustered index, right? So this is where, even though it's a very classical type of schema, it might not be the best type of scenario for a parallel load, right? And so this is almost 2-3 million. It needs to get to 3.2 million. Also, let's check the CPU usage on my laptop. So as you guys can see, basically like hovers around halfway. It doesn't really go above 70% or anything like that. It just stays there more about like 50 to 60% or so, right? So it doesn't really fully utilize the CPUs. as well. And it's over now. Okay. So let's just go down and let's check the elapsed time so we can see our elapsed time for the transfer. Well, that's really bad. I kind of drew all over the number. There we go. Okay, that's the elapsed time so everybody can see it. It's 3 minutes and 9 seconds, okay? So let's stop the debug. I have my task manager here so we can see it. And I'm just going to kick off the in-memory version now. And then we'll go into the data flow. So you guys can see the data flow right now. It's already at 1 million. Here, let me zoom in. It's at 1.3 million. It's already at 2 million. Let's go to Task Manager. Look at the amount of CPU we're burning. 93%, 94%, down to 84. Now it's down to, the regular bottom. And it's done, right? So way faster than the classic disk table because the in-memory basically is getting rid of the need to allocate space on disk, is getting rid of the need to fight for that hot page at the last end of the index. And the removal of these bottlenecks basically drives CPU use up, right? So we went from basically 3 minutes to do the same amount of work and running CPUs at 55, 60% to, let's see how long this took. It's probably like, I don't know, a few seconds. Yeah, to 18 seconds and driving CPUs to 90, 92%, right? So a big improvement in performance. This particular scenario, we've been really successful with clients in starting to use it with SSIS and other ETL tools that can use in-memory as part of their pipelines because it's just way faster to ingest data, right? So that is the landing pad. Hope that gave you guys a good idea for it. Let's jump back into the slides. So like I said, it's an easy way to dip your toes in the in-memory pool because it doesn't require you to migrate any permanent tables out of disk and in-memory and all the risks that that might convey. It's just, if you use some staging tables in your ETLs, well, then you just, convert those staging tables to in-memory tables, and that's it. Right? There's no huge risk. If there's an issue with the ETL, you can always troubleshoot it and just rerun it. So it's not like we're putting actual production data at risk. The example that I gave you guys, just to compare apples to apples, was with a fully durable in-memory table. However, this does not have to be the case. If, at any point in time you can go back and get that staging data from the source system, then you could very well have your staging tables be delayed durable or not durable at all, and this demo would go even faster. And then the other thing is that you want to make sure you maximize CPU with the parallel tasks. So I used that balanced data distributor there so that I would have 4 different streams in the package inserting rows, so that obviously is a big boost. It makes the difference in performance even bigger. I mean, if I would have run it in one core, it probably would have been faster anyway because of the lack of locking and latching. But splitting it into many cores because of the obviously multi-core laptop then makes it even better. Okay. All right, let's talk about the this is the third and last demo for today as we wrap it up. This is the table variable conversion. So we're going to compare table variables from fully classic table variable to the new in-memory optimized table variable. So let me close this down and then let's go over what the demo is going to look like. Quick tip here, I'm not going to use this for this demo, but if anyone's curious, how do I put limits on how much memory this whole in-memory thing is going to consume of my server? Well, this is how you do it. You have to use resource governor functions so that you put a limit on the amount of in-memory OLTP memory that a database can use. So here you guys can see I created a pool with a max memory percent of 65. And then we just bind that pool to the database that has the in-memory tables. And that way, the database itself will not be able to literally, for example, take over the entire buffer cache and kill the rest of the server. Okay, 60. Oh, sorry, it was 60%, not 65. And this is it. So pretty much let's take a look at how we would work with table variables classic and how we would work with table variables in memory. So take a look at the first declaration. That would be just the classic table variable. We're creating a new type as table, and then pretty average type of schema. Just we're calculating some averages of order quantities, averages of costs, how many transactions per product ID. And then we're doing the exact same thing, except the second table variable you guys can see here has the in-memory constructs, right? So I have to specify an index for it, and I have to put a bucket count. Now I know these are table variables, so usually they'll have a small amount of records. So I put a bucket count of only 8. And then I say, memory optimized is on, okay? And then I have a temporary table, not a temporary table, but a table that's going to have some aggregate saved on it as part of the comparison store procedure that we're going to use. And then like you guys can see, I have the classic version of the store procedure, and then it's the same store procedure down below, but it generally uses the in-memory table variable. It is not a natively compiled store procedure, just to make that really clear. The store procedures are both regular run-of-the-mill store procedures. The only difference is that one is using classic table variables right here, and then the other one is using an in-memory table variable. Again, it's not a comparison of this store procedure being regular and this one being natively compiled. That's not it. The only comparison is this store procedure uses a classic table variable, and this one here uses an in-memory table variable. Okay? So the way we're going to compare it is that I am going to initialize a table where I keep the current file stats for tempdb. So I can run this. And then I do a delta of tempdb stats. So I'd run a delta between the previous capture and right now. So if I run this now, nothing has happened on tempdb, so I just get zeros back, right? So let's go back into the demo. And let's do the table variable comparison. So we're going to run a classic, and then we're going to run the hackathon one. Okay. So let's kick off the classic. All right, off it goes. Again, and remember, these are both going to be regular run-of-the-mill store procedures. The only difference is one is classic table variable, the other one is in-memory table variable. Okay. So let's wait for that to finish. It should be 20,000 iterations to be done. And we're good. And if we run our delta query, let's see how much tempdb was used. Okay, so we can see here the amount of work that was done on tempdb, mostly on the transaction log for tempdb. Amount of bytes written, so this is bytes, kilobytes, about 20 megs were written on the tempdb transaction log. For this particular workload. Okay, so I'm going to save that there. I'm not going to touch it, and I'm going to do another capture on this different window, and we're going to run the delta query. So again, 0. I basically reinitialized it. Right now, tempdb is haven't consumed anything, and we're going to run the in-memory one. So let's run the in-memory one. And it has to go up to 20,000 iterations, so we're halfway there. Wait for it to be done. Alright, and we're good. And now we can just rerun our delta query, and you guys can see it's zeros, right? So results between classic, let's split this so you guys can see the vertical. Alright, here we go. Okay, so left hand here, right, the amount of writes that happen through the workload with classic table variables, and on the left hand, amount of work on tempdb with in-memory table variables. As you guys can see, it's just 0, 0, 0, 0, 0, 0, right? So this is the saving here when we go to in-memory table variables. We basically remove tempdb out of the equation, right? on a workload that is really heavy on table variables. I have particularly seen a workload where they were running dozens of thousands of requests per second, so they could reach 40,000 requests per second. It's a particularly beefy server. And they were all happening through a table variable parameter going into a store procedure. And it was doing massive TempDB contention at some points. Just because of this, because of the need of writing on TempDB even when we're using just regular table variables. So for that type of workload, this type of change would have been a big boost in throughput. Okay. So let's finish up. Table variable conversion, a second really easy way to start using in-memory. Anywhere where table variables are heavily used and hidden TempDB, that's a good spot where you want to try and see if you can convert them to in-memory table variables. If you're using temp tables too, but there's really no advantage to have them on TempDB, if you need, if they don't need more indexes, if they don't really have to have super accurate stats because they're fairly small, then you could transform those as well to in-memory table variables. And the only caveat there, especially in 2014, like I said, is if the plans don't depend on parallelism, because if you have a temp table, you could get a parallel plan, and maybe that's running really well. And then when you change it to an in-memory table variable in 2014, the plan will go back to being single core, right? So you do have to make sure that you're not replacing a parallel plan with a single core plan. In 2016, that's probably better because in-memory can now have parallel plans as well. Okay, so what we've seen today, workflow to finding the use case for this technology in your server. Understand where in the system is the bottleneck. Like we saw earlier on the slides, there are some parts where there are big benefits. There are other parts, for example, network contention, where there is zero benefit of exploring in-memory OLTP. So decide, does in-memory OLTP have some sort of improvement for where I have my bottleneck? If it does, are there any showstoppers in the limitations of V1? I need to update there, so it's the limitations of V1 and V2. If there are no showstoppers in the limitations for 2014 or in the new set of issues or limitations for 2016, for example, if you needed more than 2 terabytes to put it on in memory, which is the new limit in 2016. Anyway, if you don't find a showstopper, then feel free to continue experimenting. There's no need to waste a lot of time if you find that there's a showstopper right away, right? For example, the lack of foreign keys in V1. Like, if you can't live without that, then might as well not waste your time. Implement, test, and compare, doing an exercise similar to the one I did with the Excel sheet on the first demo. So get an idea of what type of improvements you can expect and make sure that the effort is going to be worth the work. And finally, do a capacity planning exercise because you're going to need RAM to hold that in-memory data. You're going to need storage to hold that data and Delta files. So I believe Books Online throws in a very conservative estimation of if you think you're going to have let's say 1 gig of in-memory data, then you need 2 gigs of storage. So if you think you're going to have 100 gigs of in-memory data, then you should provision 200 gigs of in-memory storage. And then growth as well. Obviously, you don't want to be in a situation where you deploy it in memory and then you ran out of RAM the very next day because you didn't really estimate your growth properly. And finally, just make sure the benefits are worth it. It's a great technology, but it is not going to be worth it for everybody. It's only going to be worth it if you really find these sweet use cases. Hopefully the demos gave you guys some ideas of where those might be found in your particular systems. Okay. All right, Jim, I don't know if we have any questions at this point.
Looks like we might have one question here.
Okay.
What out-of-memory recovery options are available?
If you run out of memory, there's a couple of options available. One, there's an actual trace flag. So you could just add memory to the server and then run the trace flag so that your memory table keeps growing past 256. But it's not recommended that you run that permanently. It's only recommended that you run it so that you can get back on your feet and then move data out from in-memory to a permanent table. And that's pretty much what the only recourse is. You gotta move data out of in-memory to a regular disk-based table, because SQL Server is not gonna page out the in-memory data. So you gotta do it yourself. You gotta move it to a permanent table and then remove from the in-memory table. There's just no way around it.
Okay, well, I don't see any other questions right now, but folks, if you do have any questions, please feel free to reach out to Warner here. He put his contact info in his slides. Again, all slides, demos, and the video will be presented later on today on the IMVC site. Looks like we do have another question. However, the box won't come up for me. One second here, Warner. Just
no worries.
Came up once, but it won't show me your question. Steve, can you message your question directly? I see that you have one up, but unfortunately the questions pane will not show. Let me see if I can reach out to him real quick. There we go. Okay. Can you catch the memory exception?
Catch, like if you're running out of memory?
Yeah, it seems like it's a follow-up to his first question about the out of memory. He wants to know if you can catch
Oh yeah,
the
you'll
memory
get
exception.
if you do get a, well, SQL has, if you guys remember in the demo, one of them I just showed, hey, you should put a limit on how much memory you can consume, and the pool limit of 60% that I had there. The engine itself also has another limit. I believe it's higher. It's probably like 80 or 85%. So it will stop giving you memory for in-memory at that point, and then at that point it'll print bunch of stuff on your error log. So any type of tool that has monitoring on the error log, for example, would be able to catch the issue and just alert DBA, for example. If it's done through like a regular client application, yeah, the client application can get the in-memory error that will just say, hey, we're out of memory here, and then you have to, again, like I said, do the corrective, take the corrective measures of moving data out of memory into this base table and releasing it from the memory of the server.
Okay.
Which is not pretty. That's why it's a big capacity planning exercise before you go to prod with really large in-memory permanent tables. Yeah.
Okay.
Sounds good.
Unfortunately, we are out of time. I don't see any other questions queued up. But Warner, thank you so much for presenting today. Really great stuff I saw. Any other questions, folks, please feel free to reach out to either myself at the IMBC site or reach out to Warner. Thanks, everybody, for your time today. Have a great day.
Thanks, everyone.